All right, what we're going to get into now is sort of building up how we can factor some of these bigger polynomials. And the first step is identifying the types of factors that we're going to pull out from these polynomials. And one tool that we can use for that is this fact that if a polynomial has a 0 at a given x value, say x equals a, then x minus a must be a factor. So that's a thing that we're going to be able to pull out. And so when I say has a 0 at x equals a, what I mean is that when we plug in a, we get an output of 0, right? It doesn't mean that 0 has to be a, it's the output at a. So this should be kind of quick work if you just follow what it says above. So we have a polynomial p of x has p of a equals 0, or has zeros at the following a values. Find the corresponding factor. So yeah, really all we're going to do for this is set up the factor using that x minus a. So if a equals 7 is a 0, so if we have p of 7 equals 0, what that means is that x minus 7 is a factor. A equals -1/2. That means x minus -1/2, which is the same thing as x plus 1/2, is a factor, right? So it's pretty easy to get these factors if you know what one of the zeros are. This would be x minus 0, or just x is a factor. And it doesn't have to be fractions or integers. If pi is a 0, then x minus pi is a factor. So yeah, it kind of comes from that quite easily. So the next step, we're going to look at what's going to happen if we have polynomials with integer coefficients, because that's going to clean things up for us quite a bit. All right, so most of the polynomials that we'll be dealing with are just going to have integer coefficients. So that means that all of the numbers that show up in the polynomial are going to be integers. So we won't have something like that example of 3x squared minus 2x plus a third, because a third is not an integer. So we're going to have this, and its factors are going to be able to be broken up in a really nice way so that they should also all have integer coefficients. And so that means that in the last example, I had one that had a rational number part of it. We should be able to fix that, basically. So we might get some rational zeros, but we can fix the factors that go with it so that we still are only working with integers. So yeah, we'll go over how we fix it. For this example, what we're going to want to do is find a factor that has just integer coefficients for the polynomial p of x if, let's say, p of -3 equals 0. So we're going to start with what we were just dealing with there. We can say that x minus -3 should be a factor. So that would be x plus 3 is our factor. And that's good, right? There's only integers in that. It's like 1x plus 3, 1 and 3 are both integers. So in that case, we're good. Now the second one, you can see we've got this rational number, and it's not an integer. So our factor is going to be a little bit uglier. So we would have x minus 1/2 is a factor. And so what we're going to be able to do is actually just fix this. So we're talking about factors. We're talking about things that we can divide out of the polynomial. We can play around with that a little bit. So we can, maybe multiply or divide by things if they're simple. And numbers are pretty simple in this context. So what I'm going to do to fix it is multiply away the denominator. And we're not like dealing with an equation or anything here, so it's okay that we will actually change the expression. So in this case, that denominator I've got is 2. I don't want to, so what I'm going to do is multiply by 2. So what I'll get instead is 2 times x minus a half, which is 2x minus 1 is also a factor. If I can pull x minus a half out of it, I should also be able to very cleanly pull out 2x minus 1 because they only differ from each other by a scale of 2. So there's no reason why I can't just sneak that out as well. Ooh, didn't mean to draw that. And then similarly, this last one, if I wrote this out, I have x minus -5/7 is my factor, but I want a cleaner looking one. So I mean, I could obviously make it a little cleaner by just writing the x plus 5/7. So I'm going to fix it by distributing a 7 through so I don't get ugly fractions. And I'll get a nicer looking factor of 7x plus 5. So that would be the nicer version. So just to give you an example of the motivation behind this, what we can do is just look at some things that maybe we're a little bit more familiar with. Yeah, so I'm just going to clean up this example. And let's say we looked at this polynomial. Let's say p of x equals, I'm going to pause it while I think about this. Right, so I've got the polynomial I want here. So look at this one. This is quadratic. We know how to deal with ones like this. So 6x squared minus 7x minus 5. I'm telling you 2 zeros here. We can just double check my work if you don't trust me. So if I plug in -1/2, I should get 6 times 1/4, right? Should be positive 1/4 minus 7 times -1/2 minus 5. So that would give me 3/2 plus 7/2 is 10 minus 10/2 minus 5 is, yeah, so that should give me 0. And then p of 5/3, if we work that out, I'll get 6 times 25/9 minus 7 times 5/3 minus 5. I can cancel out a 3 from the 6 and 9, and that should leave me with 50/3 minus 35/3 is 15/3 is 5 minus 5 is 0. So you can check my math, pause it, whatever you need to believe me. Oh yeah, those are both zeros. And then we know that we can also factor this thing. Maybe before I factor, if we think about this, what these two statements mean in our language is that x plus 1/2 might be a factor. And this one here says that x minus 5/3 is a factor. But I know that if I multiply those two things together, I don't get p of x, because if I multiply them, I get x squared. I don't get a 6. And that's because I didn't clean up the fraction parts. I didn't turn them into simple integer factors. Now, if we were to factor this thing, maybe for the sake of it, I'll do some review here. If you remember your techniques, we need 2 numbers that add up to the middle, and we need 2 numbers that multiply to the product of the first and last. So -30. So because the product is a negative, there'll be a difference. So I want a product of 30 and a difference of 7. And to me, that is 10 and 3. And then one of them needs to be negative to give me that negative product. So that works. And so this is the long way of doing this factoring. And so we should get 6x squared, and then this is where we can split up that -7 is -10 plus 3, so I'm going to split it into -10x plus 3x, and then minus 5. And then if you remember, writing it like that allows you to do what's called your group factoring. These two terms should be hopefully sort of factorable. If I take out the greatest common factor from the first two terms, I can get a 2x. And then I'd have a 3x minus 5. And then if I've done it correctly, the other term should, when I pull out the greatest common factor, it should be the same thing. Now they both have a common factor of 3x minus 5. And when I pull that out, I get a 2x from the first term and a 1 from the second term. And if you look at these are coming directly from those two things that I had said were factors, right? This is 2 times x plus a half. And the other one is my 3 times x minus 5 over 3. So when we have these polynomials with integer coefficients, the factors, even if the zeros are rational, like this one here, the factors won't have rational bits in them if we write it out in its nicest form. So we can sort of we can multiply them away and it's not going to hurt us, is basically what I'm trying to say here. So that's what we're going to be going for. Hopefully we don't need to deal with too many of the rational ones. We can sort of save them for last and not need to do ugly things with them. But if not, then you know how to deal with them.